Sorry. So let me continue with evaluations. Maybe this is too algebraic for some of you. I apologize, but algebra is one of the preferred areas of application of tropical mathematics. So let me continue with the ideas that we were discussing yesterday. So it was that I start with a map that goes from a ring to this thing, which is the tropical semi-ring. This is just R infinity mean plus infinity 0, and I said that T is the tropical semi-ring. If you look for tropical semi-ring or semi-field, this is the object that you are going to find. This is evaluation if B of 0 is 0 in T, which means infinity. B of 1 is 1 in T, which is 0. B of A times B is A plus T. And if I change this by this funny symbol and this by this funny symbol, then I can change this symbol by times. And the other one is BA plus B, smaller. At least recall that here you have to put mean BA BB. But since I am changing mean by this symbol, you are allowed to write this as B of A plus B of B. And if I just leave these two conditions, and if I change this symbol by equality, then you are going to recognize that this is the condition of a ring homomorphism. So, thank you very much. Thank you. Recall that a homomorphism is something that distributes sums and products from the start to the end. So, when we change the language or the symbols of valuation theory, and we look at this definition without these two conditions are technical, which they should be there. It is not enough to ask for that. For this also have to be present. At least my brain, I am an algebraic geometer, I'm an algebra people. I start to think about valuations as some sort of morphisms between the structures that go from algebra to order theory structures. So let me change this back to the usual notation. And afterwards, I introduced the language of semi-rings. And I told you that if B is the Boolean semi-ring, then there was an equivalence between algebra and order theory, which was the category of B semi-modules is the same as bounded semi-lattices. And the correspondence was that here you have this satisfies n plus n equals n, and you can define the order as A is more than B, for only B, and the 0 is sent to the top of the poset. So it's a maximum element, everything is downstairs. So 0 is sent to the maximum. And if you have a poset which has this the condition that the minimum exists for every pair of elements and a maximum, then the way to define this algebraic structure is to change the symbol of mean by perhaps this symbol or any other symbol that you want. For example, I define n plus n equals the minimum of m and n. And this is an equivalence of categories. If you don't speak the language of categories, it doesn't matter, it is not important. The thing is that it is the same thing to give me an algebraic structure over this. Recall that the funny thing about this is that I have a product and an addition. The product is the same as always, but the addition satisfies that 0 plus 0 is 0. I can't remember right now which was my formalism, but there is a difference in the addition with respect to F2. This is almost F2, but 1 plus 1 should be 1. And on the other hand, you have these posets. So these are posets for which the minimum of any two elements exists. And I told you yesterday that I like to think about posets as combinatorics. And of course, if you see module in one book, it tells you that this is algebra, abstract algebra. So semi-rings, this can be extended to semi-rings. And we said that semi-rings of the algebras is the same as perhaps I can put here tropical semi-rings. Were the same as totally ordered Abelian groups. So again, you have a monoid, sorry. So you have your monoid with the operation, with the identity element and the order, and how can I fabricate a tropical semi-ring? I just take this guy and add an infinity element, and then change this symbol by minimum. So I copy everything plus 0, but instead of the symbol, I put min. And this makes sense because this is totally ordered. And I put here this new operation. And on the other hand, if you have a tropical semi-ring, which is R or R plus times 0, 1, the way in which you can obtain a totally ordered Abelian monoid is just forget about the additive unit. This was the context for yesterday's lecture. Now, I am going to go deeper in evaluation, and maybe I will discuss some things about topology today. So, to make the lecture less algebraic. Have you taken courses in basic topology?
Yes.
Set theoretic topology?
Yes.
Excellent. Okay, so let's go back to this diagram. recall that tropical semi-ring was defined as a B-algebra in which this order, the order defined like m smaller than n, differently n plus n equal m. So the definition of tropical semi-ring was this order is total. What happens if I relax this condition? What happens if I don't ask a particular condition on the order of this tropical semi-ring and I just consider the category of all the algebras? What do I get at the other side of the mirror? So let me put here algebras. This is a subset because these are the B algebras that are totally ordered. I can show you that this is a totally ordered abelian monoid. What happens if I erase this condition that the order has to be total? What do I get here? I will use Spanish notation for the quotation mark for the same sign. So the question is, so I should get here an extension of this concept in which the order is no longer asked to be total. This is a question that I will ask later. For the time being, let me continue with the assumption that the order is total. Now, what is another extension that I can perform assuming that the order is total? I can assume that the monoid, this monoid is a group. Recall that I can define monoids as groups in which, so a definition of abelian monoid is an abelian group in which not all the elements are invertible. And we saw yesterday that n with the sum is an example of monoid because here the only invertible element is 0. No other element different from 0 has an inverse pair. So the lack of inverse elements may be extreme, such that only the unit has an inverse. So you can think about monoids as being defective groups from this point of view. But I think, even if this is an easy way to define what is a monoid, I think when I was in elementary school or at the college, people told me how to construct the numerical systems. Like everything starts with the natural numbers, then we can count, and then somebody came and asked the question, okay, I want to solve linear equations. I want to solve x plus y equals z, being x, y, and z elements here. As we know, some of these equations are not solvable here because we don't have inverses, right? For example, 7 plus x equals 5. This equation is not solvable here because we don't have -2. So one argument to construct the integer numbers was that this system is not perfect, but it's not complete. So So my teachers told me that if you want to solve this equation, then you go to the integer numbers. And now, in the integer numbers, you can solve this equation. And then you go with another equation without quotients. For example, A times B equals C, right? Being this and this and this integer number different from 0. And then you ask the same question. Is this equation solvable always here? And the answer is no, because we don't have quotients. So my teachers told me, in order to solve this equation, we extend our numerical system. And then we come to continuity or convergence of Cauchy sequences with the topology of Q that is induced by the inclusion in the real number. So we have sequences that we can measure in Q, we can consider Cauchy sequences, and then the same argument. Q is not complete, so we complete it with respect to the usual evaluation or usual absolute value. Then everything, all my education was, the construction of the systems was motivated by something that you cannot do. And then you construct the complex numbers, of course, because there are certain equations in R which are not solvable, so you add a cyclic extension, and you compute C, and C is in some sense the perfect base for doing mathematics. It has everything. Because completeness, topological completeness or metric completeness from R to C is preserved. But also you have algebraical closeness. This is that every polynomial with complex coefficients in one variable has a root. So in some sense, the complex numbers is like the perfect object from classical mathematics. Nothing can go wrong in the complex numbers. At least this is my vision from my education. But now, since I introduced you as abelian monoids as defective groups, perhaps it is more constructive to look at them as honest objects, not as defective ones. And this is the vision that I want to share with you today. That semi-rings and monoids and everything which is not classical is not something which is lacking power or something which is imperfect. It is something different that we must learn to handle with our own tools. You cannot use classical tools to handle this new world because this new world lacks properties from the old world. It's a discovery. But what I want to show you here is that the construction of classical mathematics is because we see a problem and we fix it. So if I would continue with this motivation for monoids, then I can say, okay, monoids are defective groups. What can I say? What can I do? Fix them. How? Transforming them into abelian groups. And then forgetting about monoids. Monoids, we don't like monoids. Why? Because classical algebra, at least in my country, starts with groups. And after that you go to rings, and after that you go to linear algebra, and after that you go to modules, you go to vector spaces. So the curricula is very stiff, is very classical. So if I somehow tell you, okay, monoids are defective groups, and I want to fix this by transforming my monoids into groups and forgetting about monoids, I am forgetting richness. I am forgetting what monoids can give me as information without transforming them into groups. So the philosophy that I am going to follow in this course is look at these objects not as defective classical ones, but as objects deserving their own existence and appreciate them for what they are. Not like wondering, life would be more easy if this monoid were a group. Or I wonder what can I do if this space was complete. Like we are always trying to fix problems. What if we don't fix it and we work with the actual structure that we have in our hands? So tropical geometry and all this kind of mathematics is somehow follows this motivation. Anyways, let me go to the concept of rule evaluation, and after that I will go to topology. But keep in mind everything that I just say here, because it's going to come back. This is a definition. Now, I introduce the concept of semi-field. Imagine that for one moment you don't have the word semi. What is a field? Can someone tell me? It's a ring in which every non-zero element
is invertible and is commutative, yes.
Thank you. So what is a semi? What can be a semi-field? The same thing. It's a semi-ring, commutative, such that every non-zero element is invertible. Okay?
Yes.
Thank you. So semi-field is what I just said. Examples. The tropical semi-field, the Boolean semi-field. Because here the product is the sum and the zero is infinity. So t minus 0 is just I with the usual sum, and this is a here the same. This is just 1, 0, 1, and 1 times 1 is 1, so 1 is in solid. Now, let me define rule evaluation, which is something that I will explain its importance in singularity theory, for example, and in recent developments in mathematics, such as perfectoid spaces. Have you heard about perfectoid spaces? Raise your hand, please, if you have. Okay, so I will put that concept over here. And I will come back at the end of the lecture. Rule evaluation. This term is optional. evaluation that I had at the beginning of my lectures. We just take, at the beginning of my lecture yesterday, S was just the tropical numbers, right? As we fixed it to be T, which is R union infinity. But now, curve evaluations, you are allowed to take any tropical semifield. What is a tropical semifield? It is a V algebra whose order is total, and also it is a semifield in the sense that any element which is non-zero is invertible, and the order as a V algebra is total. So in particular, T is a semifield, but there are many other semifields. For example, I take Z2, which is just infinite two-dimensional lattice. This is 0, 0. This is 1, 0. This is 0, 1. This is 1, 1, etc. And I will use it with the additive structure, and let me put the lexicographical order. So, a pair of integers AB is smaller under the lexicographical order to another pair CE if and only if A is less or equal than C. So, the first letter should come after before the first letter here. I'm sorry, is strictly smaller, and they are equal. Then the second letter should come before the second letter. So if you are not combined, it is an exercise to show that this is a total order. Okay? So if I give you 2 points in Z squared, you should be able to tell me which one is smaller than the other. And this is the first letter of the alphabet, and this is the second letter of the alphabet. If the first letter of the alphabet of this word, of this, you can say a word in the dictionary, comes before the first letter of this one, then this is smaller than that. So maybe this is 0, this is -2, 3, and this is 2, -2. So under the lexicographical order, you have that this point is smaller than this point. And this is a total order. So this is a totally ordered abelian monoid, which I told you that this is the same as a tropical semiring. But also this is a group. So this is a tropical semiring because every element is invertible with respect to this addition. So this is a totally ordered abelian. And in order to get the tropical semifield, I need to do the construction that it is the third time that I'm going to do it. That's to say, I have to put a new point here. And then change the lexicographical order by a tropical subject, which is a minimum. So, this is one of these objects which is more strange because this is a totally ordered 2 run to abelian group, free abelian group with an order. So maybe I can discover a new Krull valuation towards this point, towards this method. This is just to fix ideas. Let me tell you which one is the answer. So I will erase here. Let me take as K as R the field of power series in two variables. So these are quotients of rational functions with coefficients in a field K involving two variables T and U. For example, elements here can be 7U squared T plus U is 7 divided by U 5 T5 plus T8. So you have a polynomial here in two variables, you have a non-zero polynomial here in two variables, and you take the formal quotient. This is an element here. Okay? Let me fabricate one Krull valuation which is more interesting than tropical one. So let me take here just a polynomial. So I will send a polynomial to the t-adic order of the polynomial and the t-adic order of the polynomial in T and U. So, t-adic order is just the smallest exponent of t that divides this polynomial, and u-adic order is the smallest exponent that divides this polynomial in t in the first one and u in the second one. So, as we can see, there are objects that precise more information to keep track of the elements. So Krull valuation fix this for you. Maybe the tropical numbers are not enough to keep track of all the information that I want, but it doesn't matter. You can add as many factors as you want here to keep track of all the information. For example, maybe I have here another variable. It doesn't matter. I can send it to set free. And in this way, information is you can track more, you can keep more information from your algebraic objects when you go to valuation mode.